Hello, this is Engineering Statistics and Linear Algebra 18EC44, Module 4, Lecture 13, Part 1, Orthogonality, Orthogonality Basis and Graham-Smith. So first let us take the orthogonal basis and then we'll go for the Graham-Smith. In an orthogonal basis, the term here is orthogonal and basis. So basis means both the condition of independence as well as the spanning should be satisfied. Orthogonal just means it is perpendicular to each other. Each of the column, each of the vector is perpendicular to every other vector in the orthogonal basis. So the coordinate axes are naturally mutually orthogonal. Then we come to the orthonormal basis. Here in the normal basis, orthonormal basis, we divide each vector by its length to make it a unit vector. So each of the vector is divided by its length to make it a unit vector, then it becomes a orthonormal basis. So that changes an orthonormal basis into an orthogonal basis into a orthonormal basis by just dividing by length. So the vector q1 to qn are orthonormal if qit, qj is equal to 0 whenever I not equal to j, and 1 whenever I is equal to j. So the first one gives the orthogonality because they are perpendicular to each other, then naturally the what you call dot product will become 0, q1 t, qj will become 0. And the normalization, that means when both I and that is I and j are same, I is equal to j, then we'll have qit, qi, and that will be equal to 1. That is going to give us the normalization. So a matrix with orthonormal columns will be generally called Q. We call a matrix which is having orthonormal columns as Q. Example of an orthogonal basis is the E1, E2, E3 itself, which is the standard basis. E1 is equal to 1, 0, 0, 0, 0, 0. E2 is 0, 1, 0, 0, 0, 0. En is 0, 0, 0, 0, 0, 0 till the last one, and the last one will become 1. So this is the standard basis, which is orthonormal also. Then from this we can just write, if we have Q as a square or a rectangular matrix, either a square or a rectangular matrix, then it has orthonormal columns. Whenever it has orthonormal columns, whenever we have Q of this type, then we see that QTQ will always be equal to I. And that can be written like this. The Q is written like this, and Qt is written like this, and Q is written like this, and then we'll get if you multiply both, you'll get I. Whenever this matrix Q is square matrix, then at that time we call that as a orthogonal matrix. So an orthogonal matrix is a square matrix with orthonormal columns. Only when it's a square matrix we call that as a orthogonal matrix. Then Qt is Q inverse. So whenever the what you call Q is a square matrix, then Qt will be same as Q inverse. So when rho I of Qt multiplies with j of Q, the result is, again we'll have the same thing. Qit, Qj will be equal to 0 whenever they are not same, giving the orthogonality, and the Qit, Qj will be equal to 1 whenever I equal to j, both I and j are same, Qit, Qi, giving the normalization. An example can be considered like this, wherein we are taking the orthogonal matrix, which is a square matrix. Q is equal to cos theta, minus sin theta, cos theta, this matrix over here. Then the Q transpose of this is same thing as the Q inverse of this, which will just turn out to be cos theta sin theta minus sin theta cos theta. And if you take the what you call determinant of this, then we are going to get a value which is equal to 1. So Q rotates every vector through the angle theta, and Qt rotates it back through minus theta. The columns are clearly orthogonal, and they are orthonormal because of the reason that sin square theta plus cos square theta is equal to 1. So if you just take the so to say um, the value of sine square theta is equal to cos square theta is equal to 1, we generally have it as the what we call orthogonal to each other. So the matrix Qt is just as much an orthogonal matrix as Q. If you take here, the value as it is, cos square theta plus sine square theta, and that will be equal to 1. Again, sine minus of sine square theta plus cos square theta, that is again 1. So again, in this case also, it will be same. So whether it's a column or a what you call row or a column, if you take that, then sine square theta plus cos square theta will be equal to 1. The magnitude, the length of the what we call vector will be equal to 1. Any permutation matrix P. So the definition of permutation matrix is a permutation matrix is a square matrix that is exactly one that has exactly one entry of 1 in each row and every column, each row and each column, and 0 elsewhere. So only one entry in each row and each column will be 1. All other entries will be zeros, and that is known as the permutation matrix. So any permutation matrix P is a orthogonal matrix. We always see that every permutation matrix P is an orthogonal, and the columns are certainly unit vectors and certainly orthogonal because the one appears in different places in each column. So if say P is this, P inverse, that is P transpose, will just give us the exchange of the rows and columns, and we'll get 0, 0, 1, 0, 0, 1. 1, 0, 0 becomes 1, 0, 0, 0, 1, 0 becomes 0, 1, 0. And this will also be P inverse, which can be always found. Projection reduces the length of a vector, whereas the orthogonal matrix have a property that is most important and most characteristics of all. So we see that the orthogonal matrix have a very good property which the projection will not have. So projection just reduces the length of the vector, whereas the orthogonal matrix have a property that is most important. That is, the length remains unchanged even if you multiply. So multiplication by the Q matrix, uh, will just give us the length unchanged. Qx is equal to x, and this can always be proved by considering here. That is, qx square is equal to x square because of the reason that this is nothing but qx transpose qx, and that is equal to x transpose q transpose qx. So we'll have, because of this one, and this is straight away there, qtq, we know very well, is equal to 1. qtq is equal to I, the identity matrix. Hence, we'll get xtx, and that is nothing but the what we call mod of x square. Also, we see that it preserves the inner product and angle, since qx of transpose qy is equal to, again, this will be equal to this, x transpose qy is equal to x transpose y. So all inner products and lengths are preserved when this space is rotated or reflected. Now we come to the calculation that uses the special property qt is equal to q inverse whenever q is a square matrix. So or orthogonal matrix. If we have a basis, then any vector is a combination of basis vectors. So basis just means it should follow linear independence, and as well it should span, and indirectly that just means then the vector is a combination of the basis vectors. Every vector or any vector which is part of the vector space is a combination of the what we call vector subspace, then that is a combination of the basis vectors. So the problem is to find the coefficients of the basis vector. So we can write B as a combination, vector B can be written as a combination of the basis vectors x1 q1 plus x2 q2 plus dot 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 xn qn. Now to compute x1, we just multiply this equation by q1 top, then we'll get q1 transpose Q1 transpose B is equal to Q1 transpose X1 Q1 plus Q2 transpose X2 Q2, etc. Q1 transpose X2 Q2 and all that. So if you multiply that, then we'll just get the Q1 transpose Q1 will be equal to 1, whereas Q1 transpose Q2 will be equal to 0. So except the first term, all the other terms are going to become 0. So on the left hand side, we have Q1 tau. This is Q1 transpose B. On the right hand side, all the terms disappear except the what you call first term, where we'll have Q1 transpose Q1 equal to I, and that will be equal to X1 itself. So we'll have Q1 transpose B is equal to X Q1 transpose Q1, and this is nothing but value 1, and therefore we find that X1 is equal to Q1 transpose B. Similarly, the second coefficient is, if you multiply this throughout by Q2 transpose, then Q2 transpose B will give us, Q1 transpose X, Q2 transpose X Q1, that will become 0. Then Q2 transpose X Q2, that will become 1 into X2, and then the later terms are going to become 0. So therefore, X2 will be equal to Q2 transpose of B. So on the whole, we can just write in place of, X1, the value which is in place of X1, we can write Q1 transpose B. In place of X2, we can write Q2 transpose B. In place of X3, we can write Q3 transpose B. And in place of Xn, we can write Qn transpose B. So if you write that, then we'll get the B to be equal to this equation, which is Q1 transpose B Q1 plus Q2 transpose B Q2 plus dot 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 Q1 transpose B Qn. Now putting this orthonormal basis into a square matrix Q, the vector equation x1 Q1 plus dot 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 xn Qn equal to B is identical to, we'll just get this as Qx equal to B. Qx equal to B. The columns of Q, that means each one of, this, if you put it in this one over here, then, this in the value of B over here, we are going to get just this. The columns of Q multiply the components of X. Its solution is X equal to Q inverse of B. So remember that here we are taking Q as a square matrix, which is a, what you call, orthogonal matrix. Whereas if it is not a square matrix, say if it's a rectangular matrix, we cannot talk about an orthogonal matrix. So the column of Q multiply the components and its solution is X equal to Q inverse B. But since Q inverse is equal to Qt because of the square nature of Q, this is where the orthonormality enters, and the solution is X equal to QTB. So, and that is written like this: X equal to QTB is equal to the QT is written like this, and that is multiplied by B, and we will just get this. So the components of X are the inner products Qi transpose B. We see that the rows of the square matrix are orthonormal whenever the columns are. So if you just, take the length of a column, it will be 1, each column. Similarly, you take the length of each row, again it will be 1. So therefore we see that the rows of the square matrix are orthonormal whenever the columns are. Now let us consider the rectangular matrices, not the square matrix. Till now we consider the square matrices. So now we'll consider the rectangular matrices with orthogonal columns. So rectangular matrix just means we'll have m greater than m. The number of rows is more than the number of columns. The n orthonormal vectors Qi in the columns of Q have the number of rows greater than the columns. Then Q is a m by n matrix, and we cannot expect to solve Qx equal to B. So we have more number of equations than the number of unknowns. So we cannot straight away solve it exactly. So we solve it by, the only way we can solve it is by the least squares. So the key is to notice that we still have Q2, the Q transpose Q is I, that is the identity matrix. So Qt is still the left inverse of Q. Qt is, Q transpose is still the left inverse of Q. So this condition should be satisfied whether Q is a rectangular matrix or a square matrix. But however, Qt is not Q inverse in this case whenever we talk about the rectangular matrix. The normal equations are, you can just take Qt, Qx is equal to Qtb, and but Qtq is a identity matrix, so therefore we are just left with, therefore we'll just get a x hat is equal to Qtb, because it's just the estimate which we are trying to do, because we can't solve the equation. So whether Q is a square and x hat is an exact solution, or Q is rectangular and we need least square. So whenever Q is a square, then we see that we have x hat as an exact solution, and whenever Q is rectangular, we have to solve it by the least square method. So if Q has the orthonormal columns, we see that the least square problem becomes easy, and the rectangular system with no solution for almost for most V. So Qx is equal to V is a rectangular system with no solution for most V. Then if you take, Q transpose multiply on both the sides, then we get this equation, normal equation for best, x hat, in which Qt is Q equal to Y, and in this case it will be a rectangular system, and therefore, even though this is I, this Qtq is I, we will not have the value of Qt equal to Q inverse because Q is rectangular. So at that time, because this is I, we see that x hat is equal to Qtb, and this is basically solution by the least square method. So the projection of this P will be equal to Qx hat. The projection of B is this whole thing, which can be represented by this. Also, the projection can be written as, in place of x hat, we can write Qtb, and we'll get Qtb like this. So Q transpose will be the projection matrix. That's why P is equal to Q transpose is the projection matrix. So the projection matrix is now, in this case, please remember that we are having the, what you call, Q as a rectangular matrix. The projection matrix is usually written like this: A transpose A, inverse A transpose, and now if we replace A by Q, then we'll get P is equal to Q transpose Q inverse Q transpose. And Q transpose Q, we already said that it is equal to I, whether Q is rectangular or square. So I inverse is again I. So therefore, we will have this whole thing as QT. So thus, the projection matrix P is QT, which is written here itself. So let us take an example here where we try to project a point P of XYZ, which is in, three-dimensional value onto XY plane. Its projection is naturally P equal to XY 0. In place of Z, we are going to get 0. And this is the sum of the separate projections onto the X and Y axis. So Q1 is the, we'll take the standard basis 1, 0, 0, and Q2 again standard basis 0, 1, 0. And if you take the, Q1 transpose B, that is, take the transpose of this and multiply it with the B. B should be written in the form of a column vector X, Y, Z, and then take the transpose of this. If you multiply, then you just get the value of X multiplied by Q1. That is, this itself will give us X00. Similarly, Q2 is again the standard, basis vector. This will be 0, 1, 0, and Q2 transpose will be a row vector with 0, 1, 0, a row matrix with 0, 1, 0, and B is again this written in the form of a column, and therefore that will become Y. And that y multiplied by the value of q2 here, q2 is this, you'll get 0y 0, okay, 0y 0. So if you put all, this and the third one will be 0 0 0 because we have this quantity as 0 over here, then we'll get p is equal to q1, q1 transpose plus q2 transpose is equal to 1 0 0 0 1 0 0 0 0. And naturally, because this is p, then p multiplied by the value x, the value b, p multiplied by the value b will become, will give us the value of p. P is equal to pb. Small p is equal to capital PB. So projection onto the plane is sum of projections onto the orthonormal Q1 and Q2. So we come to the end of this lecture. We'll take up the lecture in the next session.